So in our last section, we learned about what moles really were, right? That it's just Avogadro's number. It's just the same as like a dozen of something, but it's a whole lot more of them so we can look at particles and atoms, right? And you even started to do some conversions based on what we already were told off the periodic table. So you already knew that there were particles, meant there were so many moles, and we did moles to grams on that worksheet. It was pretty easy because it's pretty much just straight back and forth. We just need to learn how to do a little bit more complex. To talk about more complicated conversions, we need to talk about stoichiometry. Stoichiometry is just the chemistry term for multiple step conversions, really. A lot of times it uses moles, a lot of times it actually uses balanced chemical equations. In other sciences, it might be called dimensional analysis, and I can demonstrate the base principles behind it with something you're very familiar with, time. So let's say we had 1,000,000 seconds and we needed to convert that. You might know, or you should know the equivalency statements, things like 60 seconds is equal to 1 minute. Well, you don't want to change this because you still have to keep 1,000,000 seconds. But you do want to change it out of seconds and into minutes or hopefully hours and days eventually. So you need to be able to use this. So 60 seconds equals 1 minute. This is a complete mathematical statement. It's called a true statement. Now, because it has the equals in it, it means that we can mathematically move it around. If this is a mathematical statement, whatever you do to one side, as long as you do it to the other, it's going to stay exactly the same. So I can divide both sides by 60 seconds. And in mathematics, you know, if you divide anything by itself, it becomes 1. So 60 seconds divided by 60 seconds is just a 1. And so that means we now have a new statement we can say, which is 1 is equal to 1 minute divided by 60 seconds. So since this is equal to 1, then you can essentially multiply this by 1, and you still have the same value. You're just going to be changing the units. And that works out really well because you can see we have seconds on bottom and minutes on top. So essentially what I would be doing is I would then be multiplying all of these 1,000,000 seconds by 1 minute divided by 60 seconds, which really is just multiplying it by 1, but it's going to change the dimensions or the units that we're using, right? As you can see, I would be dividing by seconds, where seconds is over here, so that would actually cancel out seconds, and I would be left with just minutes. You've probably done this a billion times naturally, knowing that, okay, if I want to turn seconds into minutes, there's 60 seconds in a minute, I need to divide by 60. That's essentially all you're doing. This just shows you the math behind the units and why it ends up becoming minutes if you divide by 60. This is the principle that you're using. And this works with all kinds of things beyond time. To give you an idea, though, you can also set up to do it multiple steps as long as you know this method, and a method that we call the railroad track method. It's called the railroad track method because you have a straight line and you have a certain value that you're starting with, in this case, 1,000,000 seconds. And then you put another railroad track down in order to block it off. And you're going to set things up with these same equivalent statements. And basically, whatever unit you have on the top, you're going to make it be on the bottom. So in this case, we have seconds on the top, so we know that we want that 60 seconds in 1 minute. And so I have my seconds on the bottom. But if I want to keep converting it, I'm just going to lay another railroad track down. And then I need minutes on bottom, so how many minutes are in an hour? We have 60 minutes are in 1 hour. Then I can lay even another railroad track down if I want to keep going. And I can say, okay, now I need hours on bottom. I know there are 24 hours in 1 day. And you have this set up to do multiple of these little multiplications or these division type things of multiplying it by 1, so you're just changing units. And you can actually see it all very nice and neat here. If you go through, you have seconds divided by seconds. You have minutes divided by minutes. You have hours divided by hours. And it's going to leave you with just days. On the railroad tracks, you need to understand that anything on top is multiplied. So you're going to multiply straight across. And anything that you're finding on the bottom, you need to divide by. Okay? Luckily, due to the order of operation with mathematics, it doesn't matter if you multiply first or divide first. As long as you divide by each of these and multiply by each of those, you're going to get the right answer. Also, if you remember, multiplying by 1 doesn't change the overall number here, so really you can just ignore all ones because you've already used the unit that you need to cancel out. So essentially what I would do to change 1,000,000 seconds into days is I would divide it by 60, then I would divide it by 60, then I would divide it by 24. This railroad tracks method is just showing you that that's how you're going to set it up. If you did that, by the way, you would get 11.6 days. Now, you probably said, well, that looks really complicated. I knew just to go ahead and do that for any kind of time that I wanted to do. You probably did, but I'm telling you this is what the why you're going to do it, because you're going to have something other than time that you're not familiar with, like moles. Remember, 1 mole is equal to 6.02 times 10 to the 23rd molecules. That's another equivalency statement just like this one. And so we can use any equivalency statement in order to convert things depending on what we have with these things. This is called the railroad method. Now that we understand the railroad tracks method, let's look back at those simple conversions we were doing before on that worksheet. So how many moles of carbon are in 26 grams of carbon? So we're going from grams to moles, right? Well, I can set it up with my railroad track method. I put what I'm given first, 26 grams of carbon, and then I needed an equivalency statement where I had grams of carbon on the bottom. Where do you get this one? Oh, you get that from the periodic table. If you were to look at periodic table, you would see carbon, element number 6, has 12.01 mass, right? That's what it looks like on its little block on the periodic table. If you remember, that mass is really the amount of grams per mole, right? So that means if it's grams per mole, that we could easily say that 12.01 grams of carbon is equal to 1 mole of carbon. And that's that equivalency statement, the same as we had with time, that we're now able to use here. And we just put the grams of carbon on the bottom. And then remember, you divide what's on bottom, multiply what's on top. The units cancel out of grams per carbon, and we're left with just moles of carbon. And so you have the actual moles. It's the same thing. It's just now we can do multiple steps if we need. Here we have just one more example of how many molecules are in 2.5 moles of a compound, right? Now, we don't have an equivalency statement on the periodic table here. We could get the molar mass of this entire thing by multiplying it, but we are given how many moles it already has of it, and we're asking molecules. So what equivalency statement we're going to use is how many molecules are in 1 mole. Remember, 1 mole is equal to 6.02 times 10 to the 23rd molecules, or atoms. And so in this case, it's molecules. And so this sets up that conversion statement. We can figure it out real easy. In our next example, we're just picking it up a little notch by doing 2 conversions, one right after the other. For this, we're finding the mass, so that would be grams is a mass, of 2.1 times 10 to the 24th molecules of sodium bicarbonate. This is just baking soda. And so to do this, we're going to have to do 2 things. First, we're going to have to turn molecules into moles. And we're going to do that with Avogadro's number and the equivalency that 1 mole is equal to Avogadro's number. We can set that up where molecules are both on bottom, so they'll cancel out. We'll be left with moles. Afterwards, though, you're going to have to find the molar mass of sodium bicarbonate. That means finding on the periodic table how much mass is in sodium, hydrogen, carbon, and 3 oxygen, adding them together so that you have the total mass for 1 mole of sodium bicarbonate. If you do that, you'll get that it's 84.01 grams per mole of sodium bicarbonate. And then you can simply set that up for moles on bottom, grams on top. You're going to end up with grams, and you end up with about 290 grams of sodium bicarbonate.